So all these factors have made me choose this topic. So I hope it's more physics oriented than mathematics. So not be talking about only Hilbert spaces, density matrices, the correlations. So that takes a lot of time. Mathematics takes some time to understand. Here, the physics probably you can appreciate easily. The physics is not complicated. Also, mathematics is not very complicated here. I hope so. So let us begin. White dwarfs. Okay. So I'll begin with the historical details about white dwarfs. Okay. So going back to 1783, the first observation was done on white dwarfs by this William Herschel. Okay, long time ago. So people were looking for stars of different kind, with their telescopes, and he discovered a hot blue hot star, but a faint star. So there's a difference between a heat and a hot star and a faint star. Faint means low luminosity. Hot means high temperature. So there's a difference. They need not be the same. The temperature, of course, is determined by the spectrum. So I'll be giving you some pieces of astrophysics so that since you're not studied astrophysics, the temperature of a star one can estimate using the spectrum. No thermometer can be put there. And the faintness is determined by the luminosity or on the earth by photometers. They will measure the photometric magnitudes and so on, how much light you are receiving from that star. So he discovered a star of a strange combination, hot but faint. This was not expected because we always expect a high temperature star to be emitting a lot of radiation. That is a normal expectation, like a black body. So this different combination. This was a puzzle at that time, and it was in the combination of 3 stars in the Eridanus constellation, and it was labeled Eridani B, this particular star. So one of triplets. Later on, it was identified as a A type of star. So stars have been identified as different classes. So spectral classes: O, B, A, F, G, K, L, M, Km, and so on. Okay. Have you heard about spectral classification? Oh, it's there in your degree, I think, degree courses. O, B, A, F, G, K, M. Okay. So the way of remembering that, I have not quote that thing. O, B, A. So O type of stars are the hottest ones. This is the A type of star. So they are expected to have a temperature around 10,000 degrees Kelvin. A type of star, and they show hydrogen lines in quite strong combination. Hydrogen strong lines. Okay. So similarly, after some time, about 50 years later on, the Frederick Bessel, the same person, the mathematician who developed the Bessel equations and so on. So in those days, mathematicians, physicists, astronomers, they were talking to one another. They were sailing the same boat. There were all kinds of what you might call all-rounders. So mathematicians used to be astronomers, physicists used to be mathematicians, and so on. So this Bessel, he was trying to measure the distances to stars, okay, by what is known as the parallax method. Have you heard of parallax of stars? Okay. So parallax. So if you observe the stars from different points, different positions in the orbit of the Earth, you see them appearing at different positions, locations. That's parallax. So while observing the most, brightest star in the sky, namely Sirius, so he found that it was wobbling. It was having wobbling means the coordinates were not fixed but varying periodically, wobbling motion. So it was a puzzle at that time, and this scientist Frederick Bessel concluded that there must be some kind of it must be a double star, some companion which we are not seeing, some faint companion. If you have a companion, then that particular, they will be orbiting around the center of mass. So if you don't see a faint one, the big one shows some small motion. So that's what he was observing. So I concluded, and he thought that it will be a double star, and he estimated the period of that combination is called a binary star as 50 years. So by periodicity, you can estimate the age. So continued. In those days, they used to do observation for a very long period, not just few years, take up for tens of years. Okay, so the unseen companion, he made a prediction, but he could not see the end of the light, the end of the day, because by that time he was no more. Okay, so the first observation of the companion to Sirius, okay, now it's called Sirius A, the brightest star is called Sirius A, okay, was seen by the son of this gentleman, Alvan Clark, in 1861, who was a telescope maker, American telescope maker. In those days, they used to make only refractor telescopes, so reflectors were also there. So refractor means lens-based telescopes, okay. Reflector or mirror-based. You know about that? It's there. Okay, refractor, in those days you can see technology was so poor. In 1861, 18-inch was the biggest telescope at that time. Okay, biggest refractor, 18-inch is so much, that's all. So now we have telescopes which are 10-meter telescopes, 10-meter diameter telescopes. You can imagine the progress. So the biggest telescopes in the world have got 10-meter diameter. So they are reflecting type, not refracting. So why reflecting are preferred over refractor? You ask the question, I will tell you about it, but otherwise I will proceed further. So refractor very hard to make, and so on. So the sun pointed the telescope towards Sirius. Always when Sirius is the brightest star, so you want to try your theories and observations on that. So Sirius star. So luckily at that time he could see with that particular telescope, that's the 18-inch, he could see two stars, one very bright one and a faint one. So that was a proof of the conjecture of Bessel, okay, that it was a double star. So you could see two stars. The bright one is called Sirius A, and the fainter one is now called Sirius B. Okay, maybe I have a picture of that. Okay, this is what it is. So here, so Sirius A is the bright one, very bright one, and also there is this faint one you can see here. That is the Sirius B. So this is Sirius B. So only once in maybe 25 years or so, they get separated to maximum extent and you are able to see. Otherwise, there will be the big one will be overpowering the small one and you will not be able to see the optically the smaller one. So there was a conclusion that Sirius B was there. So once a new star like Sirius B was discovered, found out, people start trying to figure out its properties. What are the properties of Sirius B? The new stars. So people did that exercise and they come out with the various parameters of that faint star, companion star. So Sirius mass is about 1.05 solar mass. So how do you find the mass of a star? So that is a big subject by itself. Solar mass. Okay. So what's the value of solar mass? So 2 into 10 to the power of 33 grams, so 30 kg. So like that. So this mass of Sirius B is almost similar to the mass of the sun, but luminosity was only about 3% of solar luminosity. So that is why it's faint. It is not visible in the glare of Sirius A. Okay, solar luminosity. What is solar luminosity? You have some idea? It's standard in astronomy. The solar values are taken as standard. 4 into 10 to the power 33 eggs per second. So in CGS units, 10 to the power 33 appears. So you can easily remember. Mass is 2 into 10 to the power 33 grams. Luminosity 4 into 10 to the power 33 eggs per second. Okay. So much later on, spectroscopy, astronomical spectroscopy was developed. In 1915, the Sirius B spectrum was taken, and it was then figured out to be estimated to have a temperature about 27,000, very hot. Okay, but still very faint. So what does it mean? It means it has got a very small surface, isn't it? So you can think of the light coming from a star, as being emitted from as though it's a black body. It is not a perfect black body because atmosphere is there that will absorb so many lines and all that. Approximately black body of some temperature. So if you've got a surface area 4 pi r square radius, then the constant sigma, that is the Stephan's constant, and t to the power 4. So this can be used to estimate the radius of the star. So estimated radius of this star Sirius B, this companion, was found to be around 5,500 degrees. So very similar to that of Sun. The Sun temperature, solar luminosity, surface, I mean the surface temperature is how much? Around 6,000. So like that. So it is a sun-like star, solar mass star confined in a Earth-like size. Okay, that is the difference. That is why it's called as. It turns out to be a white dwarf. So it is white means high temperature. The whiter the body, black body, higher the temperature. But luminosity depends on not just the temperature, but on the surface area, emission area. Very simple physics. So I'm told. That's why I'm telling you. You can easily understand some of the properties and features of white dwarfs. So this is a puzzle. How you can have such a small radius star holding on to very high mass like the solar mass. That is the question, puzzle. Okay, so solar mass star confined in Earth-like size, planetary size. So this is a typical property of white dwarfs, what are called white dwarfs. So you can calculate what is the mean density. You know the mass, you know the radius, you know the volume. You can calculate the volume. Mass divided by volume, you see 3 tons per cc. So if you take 1 cc of white dwarf material, it will weigh about 3 tons. So like that, extremely dense object, very high density. So very high density, how it remains stable is the biggest question. So if you have high density, gravitation is the main force that is playing on the stability of stars. Okay, so gravitation strongest force there in keeping it stable. So it will be definitely crushing the entire mass towards the center, imploding. How this remains stable? That's the puzzle. And it also calculates surface gravity. What is G? So G is 9.8 on the surface of Earth. Here 4,600 km per second square. So extremely strong gravity, pulling everything towards the center. So how it remains stable is the big question. So it is classified, it was thought to be a very strange type of star. Okay, low luminosity, solar mass, high density, remaining stable. What is the physics behind such star, or how does one explain? And it also had, if you look at the spectrum of white dwarfs, it was found to have broad hydrogen absorption lines. So that is another thing. Why only hydrogen lines are there? No other elements were found to be in the spectrum, and absorption lines were there, and very broad also. So here the physics comes in. Why do you expect a broad line? So broad line means there is a lot of pressure. Pressure broadening, high broad pressure, the temperature broadening, pressure broadening, all these things are there. So very simple physics. So there is a lot of pressure on the material, the spectral lines get broadened. So there is a lot of pressure because of gravity. So some of the properties. So about another 50 years later on, another star by the name Van Manen 2, so that was discovered. It was also having a low luminosity and high temperature, very similar to what the Sirius B was showing, and it's called Van Manen 2 star. And it occurs in the constellation Pisces. So in around 1920, when quantum mechanics was being developed, de Broglie wavelength, all this, Heisenberg principle, uncertainty principle were coming up for discussion. On the astronomy side, astrophysics side, there were big puzzles about their stability. How can you have a star which is so dense and remain stable? That was a big question. Okay. So they were named such type of star. Those three were the main things. So they were named white dwarfs by some Englishman. What is the name? Luton. William Luton named them white dwarfs in 1922. So white means hot. Of course, nowadays they need not be white in color. They can be even reddish also, yellowish, but still they can be white dwarf, small size. So over the years, they have a lot of data has been accumulated about such stars. A lot of them, about 9 to 10,000 are there. Every year, new white dwarfs have been discovered, and people are trying to understand their special properties and so on. So several surveys of sky are going on to identify these white dwarfs. So it's estimated that nearly 25% of all stars in the sky are white dwarfs. So what is the reason for that? Another question one has to examine. Why so many white dwarfs are there? So it turns out that if you study the evolution of stars, the low mass stars are in the majority. Okay? I'll show you the HR diagram. Have you seen the HR diagram? You must have seen. There even in PUC, I think, PUC University High School, HR diagram. Yeah, there it shows that a very large number of stars have low masses only, and not very much bigger than, very much higher than the solar mass. So that is why when they evolve, low mass stars evolve into white dwarfs, so a very large number. So you can try to figure out. There's a lot of physics involved. Okay, that we can all understand easily. Okay, this Arthur Eddington, great English astronomer royal of England, he declared that strange objects which show a type of spectrum entirely out of keeping, their luminosity may ultimately feature more than those which radiate according to rule. This is always the case. Only if you find an exception to your rule or your expectation, then you begin you think differently, and some kind of new rule or explanation comes out, physics comes out. So therefore, always look for difficulties or puzzles, problems. Now the puzzles are always very important, because if you solve a puzzle, then you will come out with a new physics or new explanation or new concept or something. So therefore one has to welcome them, and therefore one has to study such stars which are showing very unusual kind of spectrum. That's what it said. So this is what we expect in other areas also, isn't it? Astronomy develops when confronted with exceptions. So that is always the case, and science advances that way. Everything is according to expectation, then there is no development. So you have to welcome puzzles or problems. So problem solving is the route to development of any science. Okay. So this is some kind of a cartoon showing you the HR diagram of stars. The HR stands for two scientists, Hertzsprung and Russell. Two scientists around 1910 or so. They put all the stars in the form of a chart. Okay, place them. In this chart, we have temperature on the bottom here. Okay, going this way. Oh, sorry. Luminosity going that way. In the units of solar luminosity, solar sun is here. One solar luminosity. And temperature, I told you it is OBAFGKM. So how that name comes in, I'm not going into more details. So where is the sun here? Sun will be one solar mass and G type of star, yellow star. So sun is somewhere here. So you see large number of small stars are there compared to the big ones. Okay, that is the classification. That is some regularity was found in the temperature versus luminosity, and you can see they are also given the color code just to give you an idea. So the low mass stars are reddish in color. This K and M stars are reddish, and the O type of stars are very bluish in color. So you can see, and there are also other classifications called luminosity classes. For the same spectral class, you can have luminosities differing, giants and so on. I will not go into the details about that. So you can see what is important is there is a limit to the luminosity of a star and also surface temperature. So something like here in this particular thing, 60 solar mass is shown at the top. So you might ask the question, why stop there? Why not have 100, 200,000 solar mass stars? So that is the physics question. And similarly, when you come to the lower side at the low temperature, 3000 degrees Kelvin, okay, so that's around the smallest temperature. You can't have 1000 degrees, 2000 degrees stars. Why so? And they're also having low mass, you can small size. So what is the explanation? So one has to look for explanation in terms of known physics. Huh? Can you think of why we don't have stars having masses much greater than 60 or 100 solar mass? The question. These are all physics-oriented questions. The reason being, higher the mass, what happens? The radiation pressure increases very fast in the interior. The interior you have radiation and thermal pressure, and the radiation pressure increases very rapidly as mass increases, temperature increases both, and therefore if you have very high mass stars, then it becomes unstable. That is what is called the Eddington limit is there. I will not go into that. That is why there is a limit to the mass of the star. So I am giving you a little bit of physics also, the astrophysics also on the way. Okay. On the other side, what about the lower side? Why don't we have very small mass stars? Might ask a question. Huh? So we don't have very low mass stars, very most like 0.1 solar mass or 0.01 solar mass stars are not there. It's nuclear physics, basic nuclear physics. Huh? Because unless you have a minimum amount of density and temperature in the core, you will not generate nuclear fusion. So for that, minimum mass is required to generate that pressure and temperature, and I think 0.12 or 1/8 of the solar mass, the minimum mass required for a star to generate nuclear fusion. So these are facts which one can work out. Minimum temperature required for fusion, so it depends on the hydrogen, all this nuclear theory. So therefore, you don't have very low mass stars. Like that. Where do white dwarfs fit in this particular diagram? That is the question. And they fit in at the low left-hand corner, as you can see. This only gives only two. Now there are so many hundreds of. Sirius B somewhere here. It's a B type. Here it's shown as B type, around 20,000 degrees temperature, and luminosity around 10 to the power minus 2. That is 3%, 2%, 3%. So they occupy a certain this thing. This is a line of equal radius. Sirius B here, Procyon B, the another star. So here 10 to the power minus 2 solar radius. That is the radius around 5,000, 6,000 degrees, 6,000 kilometers. Okay. All stars, yes, they are bit. Yes, but to different extents. Different extent. Yeah, different luminosities. The low mass stars will be emitting more in the infrared. The spectrum, so there will be a little bit of visible light will be there. Optical means visible, you are saying. Yeah. So this is actually this classification is based on optical light only. Optical light only. Okay, the other form of this HR diagram where you can see more number of white dwarfs. See here more number of white dwarfs. Sirius B here, Procyon B, 1, 1 and 2 and so on. So a lot of them are occupying in this particular corner. Okay. So now after studying collecting data about so many stars, people have concluded the temperature can be surface temperature 5,000 to 75,000 degrees. So they can wide range. The central density can be million times solar value. Okay, million times, very much bigger, higher. What is solar value, central density? You have some idea. So astrophysics students should have an idea about solar properties. Okay, that is standard. Temperature, density, size, pressure, mass, magnetic field. These are all solar values are taken as standard for comparison. What would you think is the solar density at the core center? How much would you expect? Any guess? Around 100 grams per cc, like that. Okay, 100 grams, much heavier, 10 times heavier than gold. 100 grams at the core. That is what I have expected. These are come to conclude. The people have come to that conclusion through modeling and then comparison. So solar modeling is very active field, and people have succeeded in developing very good solar models. So central pressure is about billion times the solar value. So solar pressure is extremely large. Now solar pressure also people have modeled and then come to the conclusion there is about 500 million atmosphere. So atmosphere that we are experiencing is about 1 atmosphere. So 500 million of that is the solar pressure in the core, in the interior. That is very much required for these fusion reactions. The temperature of the white dwarfs is around several million Kelvin. Okay, 10 million, 15 million is common, and that is around the same temperature as that of the sun, for example. Masses from 0.17 to 1.33. So there is a limit to the mass of white dwarfs. We'll come back to this. Why there is a limit? That is the interesting part. So you do not have white dwarfs having a much higher mass than about 1.3 solar mass. And majority of solar mass are in the 0.7, 0.8, that range, radii like that. So these are all facts I'm showing you. Then we'll come back to a little bit of theory. Okay. So this is just a comparison of white dwarf and normal star, and a white blue star and a sun-like star and white dwarf. In comparison with the sun, white dwarf is extremely small and appears like that. Okay. So there are very large number of white dwarfs are found in the what are called globular clusters. So stars are found in clusters, so-called open clusters, white and globular clusters. Very large number of white dwarfs are found in globular clusters, which are spherical collection of stars called globular clusters. This is an example of M4, so another globular cluster. Why that is the case, we have to ask, because these are all old collection of stars, and white dwarfs are the old collection, the end stages of stars. Therefore, we find a lot of them in the globular clusters. So everything we have to look for an explanation, physical explanation. That is astrophysics. Okay. So again, I am giving you some kind of a chart showing you different white dwarfs and their distances and their classes and so on, masses. So you can see 0.5 to 98 and so on in the different constellations. And spectral class also they have been named to be in different classes. They have been put into different spectral classes, and the specification of that class starts with D for white dwarfs, D for dwarf. Okay, so DA 2.5, DQ, DA3. So these are the names. These are some of the names of the stars. So not every star has got a very common name or a popular name. They are labeled according to their coordinates, like this LP44113, like that. So just because you can't go on naming every star, you run out of names. Okay, so I told you these white dwarfs show a lot of hydrogen lines, absorption lines, and they are very broadened. So these are examples of DA type of stars. So DA means dwarf stars having hydrogen lines. So you can see hydrogen absorption lines are there. You can see here. Here. Absorption lines are broad lines. Unlike if you see the spectrum of sun, a very large number of absorption lines corresponding to iron, calcium, magnesium, and so on, sodium. So none of that is available, can be seen in the white dwarfs. Most of it is hydrogen lines, and there are broad absorption lines indicating of high pressure at the surface. No, Fraunhofer only. Yes, Fraunhofer only. Absorption lines. Yes, Fraunhofer. Absorption lines are Fraunhofer lines. So spectral hydrogen lines are there at the hydrogen, because that means hydrogen is there in the surface. most of it, no other material. dB white dwarfs are those having helium in the atmosphere. Okay, so helium lines are there. Okay, this is a digital. Now that digital photospectroscopy spectroscopy has come into age, developed, you can find a very fine digital spectrum of this particular stars, Eridani B. So you can see only absorption lines. These are all Balmer lines. You can see here. Here, 2, 3, 4, 5 Balmer lines. Okay, showing that a lot of hydrogen is there in the atmosphere. So very difficult to get the spectra. It would take a lot of exposure, and because the very faint stars are there, so maybe hours together you have to expose the light to the spectrometer detector. You have to integrate the light, and now that CCDs are available, it is done. Okay, possible to do. It was not possible earlier. When only photography was there, we could not get such high resolution spectra. So another example of white dwarf spectra, DA and so on. Okay, so spectral classification is there. So you see primary class. I will not dwell on this for too much. So A means hydrogen lines present, B means helium lines, C is continuous, O is helium, Z means metallic lines, and so on. Okay, B is variable. So very interesting. Even white dwarf, you expect them to be dead stars in the sense they are end stages. You don't expect them to be varying. The spectra, the intensity should not be varying, we expect. But there are white dwarfs showing variable intensity, variability in their intensity, in the luminosity, and that is a big puzzle. How that is explanation of that in physical terms is quite interesting and challenging. Okay, so I will. So this I've discussed to some extent. I will not go into too much detail. D letters and temperature index. I told you some DA3 means. So 50,000 divided by temperature gives you that number quotient. Okay. So as an example, DA white dwarf helium lines temperature etc. would be dB3. If temperature is 15,000 and only helium lines are there, it is classified as dB3. Okay. Okay, so majority of them happen to be DA stars, and dB are also there, and very small fraction of other stars dominated by carbon dominated atmosphere. That means only hydrogen is there most of the time on the surface of the white dwarfs, and a little bit of them are helium. So a big puzzle how helium is there in the atmosphere of white dwarfs. Okay, and also white dwarfs also show magnetic fields. Okay, this is to be expected on physical grounds. All stars, because they have the core, they have ions, and the rotating ions they produce magnetic field. So the sun is also producing magnetic field. The earth is also producing magnetic field. Ions rotating will produce magnetic field. So because these are formed from low mass stars, and they are compressed from low mass stars due to collapse of they are formed from the collapse of normal stars. So they are expected to have high magnetic field. So on the assumption that the magnetic flux is conserved, you have a rotating body, and supposing it collapses, then the angular momentum will increase. Conservation of angular momentum. Similarly, if the magnetic flux is conserved, the magnetic field will vary in the square of the ratio of the sizes, inversely a square of the sizes. Okay, so therefore, as you can see here, suppose initially you have a magnetic field of 1000 Gauss, and if the it goes down a factor of 100, then you expect the magnetic field to be 100 into 1000, 100 square, about 1 million Gauss. So magnetic fields of white dwarfs are expected to have about 1 million Gauss. If it 100 Gauss star, but usually 100 Gauss stars are not there. So at least 10 to the power of 5, 0.1 million Gauss stars are quite common, and some are exceptionally having very strong magnetic field. and they can have magnetic field up to even 10 to the power 9, 1 billion Gauss. So that's a big puzzle. So a lot of things are to be explained in the properties of white dwarfs. Okay. So now come to having understood some of the properties of white dwarfs, let us see how one can give an explanation for their properties, an explanation for their stability. And this was first given by this R.H. Fowler, Ralph H. Fowler, in 1927. So as you know, 1926, the Fermi-Dirac statistics were formulated for fermions, half-integer spin particles. And immediately after that, it occurred to this gentleman that it is this Fermi statistics, Fermi FT statistics, which is playing the role of creating the pressure. The particles, the Fermi particles inside the white dwarf are creating the pressure which balances the gravity. That was a big hunch, and he carried that forward, and he proposed a simplified model for white dwarfs. Okay, therefore, this happens to be the first application of FT statistics to any physical system. So that was astrophysical system. Initially, it was very simple explanation. So he said that at high densities, the matter in the white dwarf is pressure ionized. So if you go on compressing, what happens? The ions will get spilled over. Pauli's principle and Heisenberg principle, working together. So electrons and nuclei get separated, and they start moving separate independently. So you have a very big collection of high energy electrons and also the nuclei. So electrons being fermions, they obey Pauli's principle. So you cannot squeeze them any further. There is a certain minimum radius because the wave function cannot overlap too much. They start repelling. The fermionic, the Pauli's principle. So therefore, you cannot put more of them into one state, quantum state, and therefore, what happens? This impossibility of squeezing electrons any further leads to the pressure, the quantum pressure, which balances the gravitational inward pressure. So therefore, these are very quantum stars. So unless electrons behave like fermions, and fermions repel one another, obeying the Fermi-Dirac statistics, white dwarf would not exist. So that is why they are called quantum stars, isn't it? So quantum mechanical pressure balances the gravitational pressure, inward pressure in white dwarfs. Okay, so let us go into little more quantitative details. So at low energies, what happens? When you have fermions in a gas at particular temperature, they occupy all the lower energy levels because you cannot put more than two electrons into one state. Two because of spin, isn't it? So they keep on occupying all the lower levels up to a certain value, and then they start collapsing, dying out. The population reduces, and therefore, what happens? All those high energy electrons, the electrons occupying all the lower energy levels, they provide the pressure, quantum pressure. Okay, and that overpowers the thermal pressure. The thermal pressure varies directly as the temperature, directly as the density, whereas the quantum pressure varies as the higher power, 3/2 power of the density. Okay, higher power. If you have higher density, that quantum pressure takes over. This is the Fermi-Dirac statistics application, statistical mechanics. You must have studied in your BSc there, isn't it? You have a degenerate electron gas. So in the first approximation, therefore, we can think of the electrons in a white dwarf as at temperature T equal to 0. The thermal pressure neglected, which turns out to be about 1 or 2% of the total pressure. Thermal pressure is there, but that is very small because of the density being very high. Okay, so you can approximately say the probability of occupation of the energy levels up to certain momentum. This momentum, so you can take this distribution law up to this momentum, Fermi momentum, to be occupied, fully occupied, and then 0 as the initial assumption for calculating the pressure. Okay, so that is the occupation probability temperature T, Np. Because the P related to energy, E equal to P square by 2m in the non-relativistic approximation. So that probability formula you know for the Fermi-Dirac statistics. So thermal pressure varies as the gas pressure, thermal pressure, gas pressure due to the motion of the electrons, that varies as nkt or rho kt. Okay, directly as the rho and directly as temperature. Whereas this will vary, the electron pressure, the degeneracy pressure will vary a 5 by 3, not 3 by 2, 5 by 3 in the non-relativistic case. Well, we'll derive this formula. So therefore, this power, because density, as I told you, is of the order of millions of times the density of the sun. So 10 to the power of 6. So therefore, this is much higher, the electron pressure is much higher than the thermal pressure inside a white dwarf. Okay. So how do you calculate the thermal pressure? I mean the electron pressure. You have to calculate what is the number of electrons having the momentum P and what is the contribution of the pressure from such electrons, and then sum over all the momenta from 0 to P naughts, the highest momentum possible, that is the Fermi momentum. Simple calculation, I think found in even degree level books or even PG level. So number of states available for electrons, think of them as all free electrons. How much number of electrons is proportional to what is the energy density? 4 pi p square by h cube, number of states. Then you multiply by the 2 for the spin, you get 8 pi p square. No, so number of states, electron states per unit volume is 8 pi p square by h cube. Okay. So integrate over all the momenta from 0 to P naught, the Fermi momentum. So we are neglecting temperature. So you get the number density of electrons. Okay. That is Ne. What about the mass density? The mass density is rho is contributed by the nucleons. Why so? Because nucleons are much heavier than the electrons, about 8,800, almost 2,000 times. So mass density, how do you get the mass density? You have the number density of electrons, and you have to calculate what is the number of nuclei per electron, that is mu E. Mu E is the number of electrons, the number of nucleons per electron, mu E, so-called molecular weight in astrophysics, molecular weight, mu E, okay, is simply equal to A by Z, number of nucleons per electron, A by Z, isn't it? Then mH is the mass of the hydrogen. So usually they take mass of hydrogen instead of mass of proton, neglecting the mass of the electron. These are the standard approximations in astrophysics. Okay, so therefore the mass density varies directly as Ne. Okay, so what is the result then? So pressure due to electrons, that is, I told you, is responsible. That is a great idea. First great brilliant idea about the stability of white dwarf. Once you have that idea, you can work out. So what is the pressure? So pressure due to free electrons given by this formula, 1/6 of Np 2p mu p dp. So you can understand this formula is just a generalization of the kinetic energy formula. Pressure equal to 1/3 mn c square. Must have come across in statistical or thermal physics. 1/3 mn c square. Kinetic theory of gases. So there is just a generalization. 1/3 mass of the particle, number density, c square. Why 1/3 comes in, all those things. So here, so that is the 1/6 of the electrons are going in this direction, and they contribute a number momentum 2p, and at what rate? Vp momentum contribute p, integrate over the entire mass. So simple physics you can apply. So very simple integration, you can perform that, and Vp is the pressure divided by, momentum divided by mass of the electron, non-relativistic case, and in the relativistic case it is P by me divided by 1 plus P square by m square C square. So we have to use either one of them to get the pressure. So you can see simple physics, no contour integration or complex variables, nothing. Okay. So if you do that for low mass stars, the pressure turns out to be proportional to P naught to power of 5. Okay. Do this. So P naught is proportional to 1/3 power of density. So therefore the pressure of degenerate electrons proportional to density power of 5/3. So we have worked out the formula for pressure, and this has to be compared with what is the coefficient? The coefficient is this one. You put in all the factors there and you get this coefficient. The essential thing is the variability with respect to density. So that's much steeper compared to the thermal pressure. So therefore that is more dominant pressure inside a white dwarf. Okay. So this is what is called a polytropic index 3/2. So this polytrop are the subjects in the early days in 1900, people built up models of stars based on the connection between pressure and density. Okay, P equal to 1 plus 1 by m is the polytrop of index n. Okay, so that was, people thought there must be some equation of state without knowing the physical way of estimating that equation of state. So they are called polytrops, and this is a polytrop of index 3/2. People have built up models, including Eddington, and this is the polytrop of index 3/2. So once you have that pressure and density equation of state, then one has to use that to derive the pressure and mass as a function of radius. Okay. For that one has to use these equations. This is called a stability equation. This is very simple. At every radius, you have to have equilibrium between the inward pressure due to gravity and the outward pressure due to the degenerate electrons. So dP by dr equal to that, rho, and dm by dr equal to 4 pi r square rho r. So here you have pressure and density, then you have to connect these two via the equation of state. So then you get only one variable, either pressure or density. Solve that equation, differential equation, non-linear equation. So very simple mathematics here. No very complicated tensors or spinors and so on. Okay. So if you use the equation of state, because you have pressure and density, they are connected by the equation of state constant. I showed you the constant 5/3 power of the density, and with the boundary conditions. We have to solve the equation with the boundary conditions. That is, in the interior at the zero radius, that if you reduce the radius, mass should be equal to 0, and at the boundary, pressure should be equal to 0. Right? Strictly not 0, but the approximation. Okay. So use that thing and solve the equations. So it cannot be solved analytically because of the non-linear nature of the equations. So this was done by numerically by Fowler. He obtained the formula that mr cube is constant. Mass of the white dwarf into r cube is constant. So that is a big difference. In the normal stars, the mass over r cube is constant. And the average density is same for normal stars. Okay, because you have a lot of convection and radiation, and they are not degenerate. Density is so high, density is not there. So here mr cube is constant. What does it mean? If you go on increasing the mass, okay, radius has to go on decreasing, shrinking. Okay, the other way around, so that mr cube is constant. So that is the theory of white dwarf by Fowler. So if you plot here radius versus mass, you get radius versus 1/3 power of the mass. Okay. So you can try to understand how can we understand this physically. The radius decreases as mass increases. This is directly opposite to what we expect in normal stars. So it's possible to understand this physically. The answer is yes, because if you start increasing the mass, the gravity increases very much. In order to balance that, you have to have higher density. Okay, so higher density means radius should decrease. When you have higher density, the degenerate pressure increases, density to power of 5/3. Okay, so therefore, if you increase the mass, the star has to collapse in order for this to remain stable. Like exactly opposite to what you find in the normal stars. The radius decreases as if you increase the mass. So this is the curve Fowler obtained approximately with his theory of white dwarf for stability. So notice that whatever be the mass, there is a possible radius available, and it is white dwarf can remain stable at that particular radius. So around the same time, two other people, Anderson and Storer, it seems they calculated relativistic corrections to Fowler to some extent. So this was around 1929-30. So now enters Chandrasekhar. He was trying to, as you know, historically, he was trying to go to England for higher studies in 1931. 1930 he started, okay, 1931. He was born in the year 1910, so he was only around 21, just about your age. So he was trying to go to England for his higher studies. He had got all the scholarships and awards, and he was trying to go to work with only R.H. Fowler only. Why? It was a strange coincidence that R.H. Fowler had published his paper, and this paper was available in the Madras University Library. And it caught the attention of Chandrasekhar at that time, historically, around 1928 or 29. And when he was asked to find a guide, a suitable supervisor, he chose Fowler himself as a guide because he had some idea about his contribution. And he has taken the papers and the books of Eddington and so on. So he was trying to do astrophysics only with R.H. Fowler as a guide. So that was a big turning point. Accidentally, he went into the field of astrophysics. He wanted to become a mathematician, applied mathematician, because he came across this paper. He was impressed, and he had to give a choice, a guide. He had to choose a guide in England. He chose R.H. Fowler, who was astrophysicist. And while going to England, he gathered all these papers and a book by Eddington. On the way to England, he took a steamer, which took about 1 or 2 weeks at least, I think. So he started studying this paper. Deriving the mass, there is one more way. I will skip this one. Okay, skip this also. Okay. This is another way of deriving the same connection between mass and radius. Okay. Okay. So this Chandrasekhar noticed that at higher densities, you can calculate what are the velocities of these electrons. So density, you can calculate the velocity. And velocity, if density is 4 tons per cc and the molecular weight is 2, corresponding to what helium atoms, helium nuclei, sorry, then you have 4 nucleons per 2 electrons. So mu is 2. So solar mass 2 to the power 10 30 kg. So it turns out the momentum is 1.29 mc. That is mass of the electron into c, which means the electron velocity is nearly 63% of velocity of light. So that means the electrons have to be are relativistically moving. They have got relativistic velocities inside the white dwarfs. Okay, at least in the interior portion, most of the interior portion. If it crosses 20 grams per cc, okay, so electrons become degenerate and relativistic. So it flashed upon Chandrasekhar that these electrons have to be treated relativistically, not just as not relativistically as done by Fowler. So he started working on that. He used the other equation of state connecting the pressure and density. Okay, so therefore he started using this. So again, this is very simple. At that time, it was quite complicated, a new idea. The new idea is more important than the mathematical steps. Okay, so we have to use the velocity as p by m into that factor. So this is even slightly more complicated than the other integral, but it can be done. Okay, all these things are various steps defining the variables and so on. So if you do that, so you get the before coming. So this gives you a parametric equation of state. It is not a simple p equal to rho to the power of 5 by 3. You don't get. So you get here a density proportional to px cube and pressure related to A into Fx, this quantity. So more complicated connection between pressure and density, parametric equation. So one has to solve it a little more ingeniously or laboriously. And in those days they didn't have calculators, computers, they had hand calculators. He did that and he came up with this result. Schematically I have shown that is radius versus mass. SC means S Chandrasekhar. Okay, So he got that full line, the black line there. Okay. So as you increase the mass, the radius decreases in the beginning as shown by Fowler, but later on it decreases very fast and goes towards the value 0. Okay, radius decrease becomes 0 at one particular mass, and that is now called the Chandrasekhar mass limit. So according to his theory, which is definitely much better than Fowler, so there is a limiting mass that turns out to be around 1.34 solar mass, 1.4, depending on the composition. Okay. Okay, this is a photograph of Chandrasekhar 1930 when he was 20 years old. So he had not even got the PhD. He was going for PhD. By that time, he had come to this conclusion. The mathematics was simple. The idea is new. The physical idea is more important. So he was trying to explain something there. Maybe equation of number of states like that. So nowadays, one can solve those equations using computer within a matter of few minutes. Okay, you give the differential equations and ask for the solution. Given the initial conditions, final conditions, and you get these curves. Very simple. One can do with computers. Okay, non-degeneracy n is 1.5 polytrop. Chandrasekhar theory gives you the red line. So mass radius versus mass, like that. So one can easily get now. Any high school student or college student can easily solve those equations. Those days it was a big thing. Okay, this is an extract from his book. The book name is Stellar Structure. Stellar Structure is the name of the book he published in 1937 or so, I think. So where he showed, he draw the diagram of how the radius here as a function of mass. So radius goes on decreasing like that, becomes 0. Okay. So that was a big discovery or big event, big explanation or discovery at that time, which was debated hotly and not accepted in the beginning by the astrophysics community. In particular, Eddington himself was his teacher to some extent. He was giving courses which Chandrasekhar took. He did not believe in that kind of a conclusion. So Eddington expected some kind of a law of physics which would prevent the collapse of a star. So some collapse is not possible. That was a belief. So or prejudice he had. So it was not accepted in the beginning. Even though very simple mathematics at that time, and physics also very straightforward. Not much complication. Okay. So if you put in all the constants, so here you find the Chandrasekhar limit formula for the mass limit, MCH equal to etc. HCG that. It depends only on the fundamental physical constants. And also you can notice that it depends on H and C. Whenever you find a formula depending on H, it means a quantum effect is there. And C, relativistic effect is there. So gravity. So fundamental constants like H, C, G and mass of the proton. So these are responsible for defining the Chandrasekhar limit, mass limit. Therefore, it's very fundamental and has to be taken seriously. Okay. So it seems Landau at the same time, Lev Landau, Russian physicist, also arrived at the similar formula independently, but probably he did not publish that. Okay, so for mu equal to 2, you get the 1.44 solar mass star, isn't it? Okay. So then we can think about various other possibilities. Once you have the basic idea in place, basic theory, concept, you can think of various modifications, improvements to theory, like the presence of rotations. What happens if stars are rotating? Then of course you require a higher mass limit, isn't it? Because rotation will add extra repulsive force, so therefore you require higher mass in order to counteract that. So people have worked out these models with rotations. In fact, Chandrasekhar himself worked on this for his PhD thesis. His PhD thesis was on the polytrops of stability of polytrops stars with rotations and distortions and magnetic fields and so on. So that was PhD thesis which he submitted in the course of 3 years. Okay, so once you have a polytrope of some index, what happens? It will be rotating, it will be distorted, and it has got magnetic field. So one has to write down general equations. So he was a very good mathematician to start with. So he wanted to become a pure mathematician. His father said, no, you will becoming a pure mathematician, you want to get a job. So go for IAS, ICS. That was his recommendation, the father's recommendation. So in those days, the administrative job was the most favored job. You go for ICS, you can permanently you get employed, no questions asked. So therefore, that was the suggestion of his father. But Chandrasekhar did not like that. He was more inclined towards science, especially mathematics. So he chose applied mathematics as his field. So he was very good at mathematics, solving differential equations and so on. So applied this rotating white dwarfs also. People have worked out. Refinements to the equation of states. Once you have the equation of state, then you think of all the other possible refinements you can think of. It is not a pure only electrons gas. Okay, so there will be Coulomb repulsion between the electrons. One has to take that into account. Okay, so that was done by, as I told you in the beginning, D.S. Kothari, one of the professors at Delhi University, who later on became the chairman of UGC. D.S. Kothari, 1931-36. He published some papers. And exchange correlation effects. So you have exchanges, nucleons and so on, correlations. I don't know the details about that. Auluk and Mathur, they were again Indians. And at very high densities, this nuclei can form some kind of a condensed state. That was proposed by a Russian scientist. So people work on that state. Okay, so on. And temperature effect, how one has to consider. You want to make it even more accurate. Then the dependence, equation of state can depend on both A and Z. It's just the ratio. Now the nuclear effects can be taken into account, and also inverse beta decay. So all these things have been done, and there are some more things can be done. So inverse beta decay means what happens? You have the high electrons, high energy electrons, and you have nuclei, protons. At very high energies, they'll start combining to form neutrons. That is inverse beta decay. Okay, electrons will combine with the protons to give neutrons. That is inverse beta decay. Neutron to proton, electron, that is something. So that can happen, reduce the number of electrons. So pressure is therefore reduced. The electrons are not too many are there, so it can collapse easily. Okay, so all these things have been taken into account. And Chandrasekhar himself later on, 1964, when he was 54 years old, he applied GR, general relativity, and showed that there can be some instability at very high densities. So GR has this feature that if you have high mass and high pressure, so they can contribute to mass. The pressure can contribute to mass. That is a very strange thing about GR. Okay, the pressure itself can act as a mass, and therefore it may lead to instabilities. So these are some of the things. I have not gone into detail, but I have know a little bit about them. So what is the observational evidence? They have been plotted. Okay, observed only few number of them have been observed. It's hard to find the masses and so on. So depending on the core, your Sirius B is here. Solar mass and radius have been determined. So depending on the iron core and Procyon B, 40 Iridiani B and so on. So all of them lie well below 1.4 solar masses. So far, no white dwarf has been found to have any mass over 1.4 solar mass. It stands. The limiting mass stands well justified. Okay, here's another data of white dwarfs and their radii. Okay, so you can see all of them are definitely 1.4 is a solar mass limit, so theory holds. And there were even some questions. There was a question in the book himself. He raised a question: what happens if the mass of the star exceeds this limit, 1.4 solar mass, white dwarf? So he could not imagine what would happen. It would collapse. He thought maybe it will end up in some other very condensed state, which we cannot predict. So he was hinting at the possibility of a black hole appearing. We have much higher mass. What happens? It can collapse further, leading to the formation of a black hole. So the idea of black hole was there, but they did not take it very seriously forward. So but some people in the popular literature, they say Chandrasekhar predicted black holes. That is not the case. He did not predict. He speculated. We don't know what could be the possible states of masses beyond this 1.4 white dwarf, beyond 1.4 solar masses. It's very hard to conjecture. If you conjecture, it may be too wild conjecture. Ah. 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 Yes.
Suppose I have taken them and their
yeah.
that would lead to some other.
Yeah, some other star, but they are not.
High energy. That is dominant. Yes.
Yes.
But this got some other level.
Yes, certainly. But they are not found in normal stars. The muons and tauans, they are not found in normal stars. They are normal material. The so-called normal material. They are not stable. Yeah, you don't find them in the normal star, normal matter. Muons are very unstable, as you know. They will decay, and they are not found in normal stars. A small amount can be there. Some cross section of electrons can be there, but that is very small. So formation again is all what is called stellar evolution theory. So it is expected that the sun-like star would evolve towards red giant stage when all the hydrogen is gone. Okay, so it becomes cooler and bigger, and then it is possible that again some kind of a collapse is possible due to helium compression, and then it comes back to higher temperature like that. So undergoes several oscillations from and towards the main sequence, and finally it will then explode in the form of a planetary nebula when there is no more energy available in the core for that to keep the core intact. Okay, so therefore what happens, the surface of the star will be blown away and what remains would be the white dwarf at the core. So that is the theory of formation of white dwarfs. So this is some kind of cartoon showing that you have a hydrogen as an envelope, and the core you have the helium, okay, heavier, and it is still stable. Helium burning is there. Then the high temperature, the radiation pressure is expanding, and it becomes cooler as it expands. So these are the theories of. So this is an example, actually, planetary nebula. So what you find at the core, is what is the white dwarf there, the core, and then the gases are around that is planetary nebula. So all these colors will indicate what are the materials which have been thrown away from the envelope. Okay, so cooling, what happens to white dwarf once they are formed? Because they don't have any nuclear energy available in the core. So otherwise there would be much, because of that high density and temperature nearly that of the sun, if nuclear energy was being produced, then they would be definitely much more luminous than what you find. So that is proof that nuclear energy is not taking place inside the. Why that is not taking place? Because you have inert substances like helium or carbon, and they require a much higher temperature for them to fuse. Fusion is not possible. Okay, so therefore, what white dwarfs do as a function of time, they just keep on getting rid of the temperature energy from the core through the surface as emissions. That's what they do, and because they are of high density and high conductivity, the conduction mechanism is the main thing in removing the energy of the white dwarf through the surface. So this theory has been worked out. It's quite straightforward in the sense you have a very hot solid-like thing. Okay, so density, we know the profile of density and profile of temperature, and if you can estimate the conductivity of that particular material, we can work out how much energy is being passed out of the surface. So people have worked out these models of white dwarf cooling, and they have come out with this kind of a distribution of temperature versus radius. Okay, so temperature varies at the core as T to power 7 by 2 power of the central temperature. Luminosity varies as 7 by 2 power of the central temperature. So again, the physics is not very complicated. You have material, very hot material, having a high density and temperature, and density varies. So at every stage, you have energy being transmitted, conducted away. You can calculate how much finally it comes out of the surface. So that temperature, therefore, as a function of time, how the luminosity varies, people have calculated. So luminosity varies very fast in the beginning, and like Newton's law of cooling, same thing. But here you have a variable density, conductivity varies, and so on. So one has to take into account all the variability. So again, you can see the physics is not very complicated. One can take it up as a project to work out all these things in detail. So in the beginning, very fast variation in temperature, decrease, and later on it flattens out, and it will stay there for a very long time as a low luminosity faint object in the sky. Finally, it will end up as a black dwarf, so to speak. Okay, electron. This is what I said. Lifetime of the order of 200 million years. That is the expected lifetime. So it depends on the size and initial temperature of the white dwarf and so on. Okay, so another people have estimated, the distribution of white dwarf as a function of luminosity. So people are trying to use this as a estimate of the age of the galaxy, because if there's sudden fall in the number distribution of white dwarf, that means there were no white dwarfs previous to that particular age, and we can go back to using the cooling effect, cooling rate, you can estimate what is the age of the white dwarfs for that to be the case, and that would be giving you an upper limit on the age of the galaxy. So people have used white dwarfs, they are estimating the age of galaxy. Okay. Okay, these I have mentioned. So coolest temperature, if you white dwarf, coolest is about surface temperature 3900. So people are looking for different types of white dwarfs and their properties and stage properties and so on. And they expected that if carbon core is there, then one expecting them to form a kind of a diamond lattice. So that expected to be there as a condensed white dwarf. Okay. So one more possibility is there. Supposing white dwarf is found in a companion star. These are very commonly found. Suppose white dwarf, the core is there, a binary combination. Other normal star is there, and it is evolving. It's possible that the mass emission, accretion from the normal star onto the white dwarf is possible. This can occur, leading to kind of a runaway process of explosion on the white dwarf, leading to what are called supernova, one type of thing. Okay, so like this is a pictorial model. So you have white dwarf there, accreting matter from a normal star, red giant star. So when it's falling onto white dwarf, the white dwarf cannot take it any further, and it explodes and as a supernova. Okay, so the cost type 1 supernova, type 1A supernova from white dwarfs, and these have been observed in different distant galaxies, and they are used as standard candles, because people have estimated if such a white dwarf of let's say 1.4, if it reaches 1.4 solar masses, if you go on still adding more mass to that, it will collapse, explode and collapse into supernova with a neutron star at the core. So giving rise to a very standard distribution of luminosity versus temperature, time, and that can be used as a standard candle. Standard candle means you require in cosmology distant indicators. So parallax method doesn't work. So many other methods don't work. So you require a standard luminosity object in the sky, and you estimate what is the observed luminosity. Then from that you can estimate what is the distance of that particular galaxy. The galaxy estimation, the distance estimation is very important in cosmology, and for that white dwarfs have been used as principal tools. Okay, so Some more thing about that. Okay. What are some of the puzzles? Of course, no subject is, of course, fully complete, understood, fully understood. Maybe I is not missing some of the questions that remain, unsolved problems, is not listed here. So one of the unsolved problem is how you can have variable white dwarfs, so-called DAV stars. So white dwarfs show some kind of variability. So how can one explain the variability? One can think of that as some kind of star spots on the white dwarf and that variable. And then the DB white dwarfs, how helium white dwarfs are possible, okay? How the helium begins to appear onto the surface. So these are some of the questions that remain unanswered and people are working on that. And also the white dwarfs can form, white dwarfs can be used as the material for testing general relativity. Why so? Because they provide very strong gravity on the surface gravity. So as I was mentioning, what happens, the spectral lines from the surface will be redshifted. So it takes away an energy, very simple to understand. So any radiation, it has to escape from the gravitational field of the white dwarf. It has to lose some energy, therefore it appears reddish. Of course, one can work out the details, how much is the redshift depending on the gravitational field of the white dwarf. So therefore, this red shifting of white spectral lines has been used to test the Einstein theory of relativity. So like that, many of the questions still remain, and still they are being studied. Okay. So I think that's about it about white dwarfs. I have stopped, ended right on time, 5 minutes remaining. So if you have any questions or comments, you're welcome. So simple physics and simple mathematics can explain this quantum star. Without quantum effect, white dwarf will not exist. And even more quantum features are found in more compact objects. What are they? Neutron stars. Even more stronger quantum effects are there. Superfluidity, superconductivity, all those things are present in super neutron stars. They are much more difficult to understand because the composition is not very simple, like in the white dwarfs. So many nuclei and superfluids, ions, all present to varying extents. So more complicated. The equation of state is also not very clear in the case of neutron stars. Here is very simple. So you might. Everything possible. Yes, yes.
So, like how you show from graph, mass,
yes, yes.
radius, Gibbs potential shows from different features.
Yes, yes, definitely. Yeah, they're possible.
Forward.
Yeah, if you, that is the next level approximation. Temperature is not zero. You don't put it as zero. Next level, you have to calculate. People have done that.
Because it's only temperature varying.
Yes, yes.
But entropy is not seen.
Yeah, it's not shown.
So, kind of.
Yeah, so many corrections. Variables are there. The biggest puzzle is how to explain variable white dwarfs. You don't expect white dwarfs to vary. What is the mechanism? Maybe the interior is fluctuating. Still, it may be undergoing some kind of phase transition from hydrogen to helium. So oscillations taking place. So that possibility is there. So I don't see clear explanations. Variable stars, variable DAV. So you might get interested in these topics and like that. A lot of physics is there, less mathematics compared to what you saw in the entanglement case. There's more abstraction and less physics perhaps. I don't know. Physics part is not explained there. The spatial part. Okay.
One is on I hope